Hello students, today we will start with the introduction to Galois field mathematics. This why we are entering here is we have learnt a lot about the circuit design perspective of the generation of the codes, p-n sequence codes and as well as the maximum length sequence codes through your linear feedback shift register architecture. But we have also discussed little bit about the mathematical analysis we have done. We have discussed little bit about the way the output codes and the bits of those codes are generated. But we have not really gone into deep philosophy of designing and devising these codes and that from the fundamentals of the mathematics. In future, if you try to design some code for secrecy of and it will be for your own design, then you need to understand that how to start, what is the deep root of the mathematics, from where actually the understanding and the framework should start with. To bridge that gap, we will learn today a little bit about the Galois field mathematics, and we will try to link up all the terms that usually is used for the code generation. Galois field is a finite field where you will see all the contents or the elements all the elements of that field contains the finite numbers. So, these finite fields are basically used for your code analysis, your analysis of the periods, autocorrelation, cross correlation, generation of the p-n sequence, p-n random sequences, and also the linear feedback shift register architecture, nonlinear sequences. We will specially see in the later modules how these finite fields are really very important for the nonlinear code generation. We will also link up the concept of the polynomials and the finite fields to the linear feedback shift register architecture at the end of the understanding of Galois field mathematics. So, this is a one usage scenario where the finite fields are utilized for all these purposes, and but it has another important application in generating and in devising very lot of cryptographic primitive algorithms. I have given here some of the example of those cryptographic algorithms. For example, the Diffie-Hellman key exchange algorithm, digital signature standard algorithm, EI game public key encryption, elliptical curve public key cryptography, LFSR based public key cryptography. These are some of the examples where finite field is a fundamental concept from where we start with. The finite fields and these shift register sequences, they are also used in other areas of the communication. For example, for code division multiple access communications, in devising the forward error control codes, the FEC, which we call the FEC, and those error control codes are designed to give the protection against your channel burst errors as well as the channel errors, and all the whole family of the forward error control code, starting from your block code to all the codes that you can name of, the convolution code, the RS code, the concatenated codes, the LDPC, which is mostly used in the modern communication systems. The generation and the algebraic architecture of all those codes roots down to the understanding of finite fields. It is beyond the scope of this course to show you all the aspect of the finite fields and its application to those generation, but we will definitely relate the finite field, its relation of the finite field to the LFSR architecture and nonlinear code generation architecture. So, from now onwards we will talk about some specific algebraic architecture, and those algebraic structures and the architectures will be named as the group, ring, field, polynomials, etc. But before describing their architecture, we need to understand some of the definitions. So, we will use this following notation. Number 1, this is n, which will be the set of normal natural numbers, z set of the integers, q the set of the rational numbers, r the set of real numbers, and the set of the complex numbers. Okay. Natural number, integer, rational number, real number and the complex number. So, now we are starting with the group. Before entering into the algebraic structure of group, we need to understand what is the meaning of binary operation, that we seldom used in the digital communication, but what is the mathematical meaning of it is like this. Let us consider that S is a set and there are S cross S, it denotes another set which is basically constituted by taking all the ordered pairs S comma T, which where S and T they belong to the original set S. So, I started with S, I took all the ordered pairs who belong to S and I have put all the ordered pairs into another set which is S comma S cross S. So, then the mapping of this S cross S to S, if I do some mapping from S cross S to S, will be called a binary operation. Remember one thing, under this definition of this mapping and the binary called binary operation, we require that for the image of all the components of these ordered pairs S comma T which belong to your S cross S, they should also be present in S. If I do a mapping from S cross S to S, then all the elements that belong to S cross S, that are the ordered pairs, must have an image on the S. That is the assumption that has to be done. We call it the closure property. So, what we learned? We learned that what is a binary operation and we learned what is the closure property of an operation. So, now the algebraic structure of the group can be defined. Set now S and together with is one or more than one operation that we are declaring here together with S, I mean that operations are running on S, is combinedly called algebraic structure. So, I have a set and I have one or two binary operators, and so those binary operators together applied on S together will be called as a group. We can now set the definition of this group. A group is a set with together with this operation star, the operation is symbolized as star, and so the star operated on G will form a group if and only if the properties, the following three properties hold good. Property number 1, the binary operator, this star, it should be associative. That is, suppose I have three elements which belong to G. For them, if I give the operation like this, means B operated B with C, B star C, and then A star B star C should be equivalent to A star B star C. And there should be an identity or unit element called E in G in such a way that for each and every element A who belongs to G, if I do that operation, if I apply the binary operator in between A and this element E, it should revert me back the which is equal to E star A also, it will revert me back the element A. If it holds good, then we can declare E is the identity element of the group G. And the third element, the third property says that for each and every A that belongs to G, there should be the another inverse element present in that group G, and that such a way that A operator with that operator operating on jointly on A and A star will give you back the identity element E. So, hence we have two unique element associated with G. One is the identity element and another is the inverse of each and every element whoever is present inside the group. So, with respect, and G is actually generating the identity element and this inverse element with respect to a specific operator called the operator star. So, group with its binary operator and its identity element, sometimes we prefer to write three of them jointly to denote a group, and we call it a triple. And if we find that for all the elements say A comma B who belongs to G, I am finding a property like this, that A star B is equal to B star A, then we can call that this G is a abelian group or commutative group. And from this definition, the identity element E is definitely an unique element, and inverse element also is an unique element associated to a specific group. For simplicity, now we can proceed from now onwards, saying that this instead of writing A star B, we may use that A B, but remember that this A B does not mean that the normal multiplication that we understand in the conventional arithmetic. Similarly, actually if the group is my abelian group, then for the operation of instead of writing A star B, and we can write A plus B instead of writing A star B, and we can also write minus A instead of your A inverse. And this additive notation, using this additive notation is instead of my A star, the operator, we can't write this A plus B also. So, in the whole Galois field, you will see that the elements are either said by A B or A plus B based on the operator is multiplicative operator or it is a additive operator. Another important part to understand is the associative law that guarantees that the expression such that A1 to A in the way that you are writing, where all the AJ's belong to G and J is varying from my I to N. These are unambiguous. So, whatever we insert the parenthesis, this expression will always represent the same element of the G, of course. Now, we are coming to some more understanding. Suppose we wish to indicate the N composition of an element A. A is belonging to G with itself, and this small n can have it exists between a capital N, any value within 1 to capital N it is. So, we will write the n fold of A if we utilize the multiplicative notation, and we call it an n factors of A, which is basically A multiplied by n times, and we call it the nth power. Okay. And if we use the additive notation, then it will be like as A plus added it is n times. So, we call it n summands A, and we will be ending up with n into A, and we call sometimes it is an n times A also, like the conventional system. So, some customary notations here, some small operations we have shown. So, for multiplicative notation, A to the power minus n can be equivalent to A to the power minus 1 into n, and equivalently here it will be minus n into A, which is nothing but n into minus m. Here actually multiplication of A to the power n into A to the power m will be given by A n plus m, whereas in n A plus m A it should be is equal to n plus m into A. Here we are ending up with A to the power n whole to the power n, which is equal to A to the power n into m, and here it is ending up with m n A, which is equal to m n of A. For your n is equal to 0, which belongs to the group integer group, and we adopt that A to the power 0 is the identity, it is the identity element by convention in case of our multiplication notation, and 0 into A, which is equal to fundamentally 0, this is the additive notation, where this 0 will be the identity element with respect to the additive operation is equal to additive. So, once we understand the definition of the group, so we can now map that all the integers, the group of the integers, the set of the integers with respect to my positive, I mean plus addition with respect to additive operator, and with respect to 0th identity element is a group. A set of my real numbers with respect to additive operator and 0 identity element is a group. All the real a set of real numbers with the multiplicative operator and with our identity element 1 is also a group. Now, let us define Zn. Zn be a set of the remainders of all the integers of the z when it is divided by the number n. So, it is a modulo n. Zn is the modulo n, it is the integer with the modulo n of z, I should say, and then Zn star is the set of the non-zero elements who are co-prime to n. The definition of coprime is such that suppose n is a prime number, then actually any number between 0 to n if you pick up, and if you try to find out that any number and that number let be a, then you will see that the greatest common divisor in between this number a and n is equal to only 1. If this happens, then we say that a and n they are coprime. So, in this situation, when Z n star will be the set of the non-zero elements which are picked up from Z n, and then you will see that all the elements the coprime, the elements of this is constructed in such a way, the elements of C of the Z n star, they are the coprime to n. Let a plus b, a b, which we have already defined, they are the ordinary sum and products. If that is the situation, to then for we can actually nicely construct this Z n and Z n star with respect to some known can construct some known groups like this. Z2, it is called the remainder when the modulo 2 operation is run over the real numbers with respect to my positive operator and my 0 identity element is a group, and this is also of modulo 6 operation with respect to my positive operator and 0 identity element, like this Z5 plus 0, they are all the groups with respect to addition. And then this Z5 star with respect to my multiplicative operator and my identity element is equal to 1, it forms another group with respect to the multiplication. So, now we can propose some theorem. This theorem is with respect to this notation, we can propose that Z n plus 0, I mean with modulo n operation over the real numbers with additive operator and identity element 0 will form a group of any positive integer n, and which is called as the additive group of the integers modulo n. So, it will be we have to prove that this forms a group, and again all the prime numbers, if p is a prime number. So, Z p star with multiplicative operator and identity element 1, it will also form a group for any prime number of prime, which is called the multiplicative group of the integer modulo p. We have to prove that this is a really group, we have to prove that this is really a group. So, we will do it in the next slide. So, in order to prove that it is a group, what we need to do, we have to prove that the with respect to the binary operator, the elements are associative. We have to prove there exists an identity element and there exists an inverse of that. So, our identity element, the inverse element as well as associative law, we have to prove for both of them to consider that yes, the fact is true that these will form a group. And we have seen a fact from the definition of the coprime just now that I told, that if p is a prime number, then for any integer a which belongs to the 0 to p, a and p will be coprime, because you will not find the greatest common divisor between a and p apart anything apart from than a. So, always it will be equal to a only, and moreover you will also find two other elements u and v, such that this au plus pv will be always equal to 1, where this u will vary between your 0 to p, u and also the v will vary between 0 to p. So, now we will come back to the proof of the proposition that we did in the last slide. So, let a mod n denote the remainder of a when it is divided by the number n, and if the result of an addition or the multiplication of the ordinary is to be reduced mod n, and then the same answer is obtained if some integers which appears are reduced mod n during the intermediate steps of the calculation. So, what is the meaning of this? Suppose I am getting a result after the addition or the multiplication of any ordinary number which is reduced to mod n, and then same answer you will always get is obtained if some integers which appear are reduced mod n during this intermediate calculation of this ordinary addition or multiplication of the number which is reduced mod n, you will get actually the results are becoming same. Then now for my two elements a and b, who are belonging to Zn. We will start with the A plus B, and this is with respect to the first one. So, our target is to prove that this Zn with respect to plus and the 0 is a group. Here we are. So, suppose this A plus B is a remainder on the division by n of the ordinary sum of A and B. So, definitely if it is a remainder, definitely the remainder will belong to Zn. It is an integer number, and if I take any 3 number A, B, C which belong to Zn, and then now consider that A, B, C all are integer, then if I operate in the normal operation, if addition operation, if I do for normal addition operation, it holds good. If it holds good, then it should be also hold good for this, means A plus B plus C should be also equal to A plus B plus C for when mod n operation is going on. For normal operation, if it is true, then with the mod n operation it will be also true, because we have already proved that this mod n will be, after mod n operation, that number belongs to the same set. So, any A that is belonging to the Zn, so it proves the first one proves the associative law with mod n operation. Second one, if A is belonging to the Zn and A plus 0 is equal to 0 plus A is equal to A, of course, it will be always. So, 0 is always the identity element in Zn. So, identity element is also found. Now, for each and every A that belongs to the Zn, there should exist a positive integer B that also belongs to this Zn, such a way that when this operation is going on, it is equal to n. If n is, note that n is equal to 0 mod n. So, A plus B is equal to B plus A, whatever you do is will be equal to 0, and such then in such a situation B is definitely a inverse element of A. So, hence you could find the inverse, the identity element, and you prove the associative law for this algebraic structure Zn with respect to plus and with respect to 0. Hence, it can be declared as a group. Let us see for the other one. Zp is the set of all the prime numbers. So, let A and B belongs to P, and AB is the remainder of the division by P of the ordinary product of A and B. So, again going by the same logic, AB should belong to the set Zp star. Now, for ABC 3 elements taken from the Zp star, we consider that A, B, C are the integers. If it is integer, then A into B, C should be equal to A, B into C, and it also true that the same going by the same logic, this can be also written after modulo P operation, they all belong to the same set, and hence it satisfies the associative law. It is obvious that 1 is the identity element because it is a product. So, wherever you go, 1 will be the identity element for this whole set. And for any element A, Zp star, which is a prime number, according to this fact 1 that we have declared earlier, there should exist 2 other numbers such as u and v, such that u plus pv will be equal to 1, and where u will be varying between 0 and p. And remember there one fact that AU plus PV is also mod P, AU mod P is equivalent to AU mod P. So, hence actually we will get AU is equal to 1 mod P, which will further give you that A inverse is equal to U, nothing else. So, which is also belonging to Zp star, such that the U is the inverse of this any element A in Zp star. So, Zp star is also having identity element which is equal to 1. It follows all the components, all the elements of this set follows the associative law, and we have proved that there exists a inverse element U for this set. So, hence Zp star with respect to your operators dot and with identity element 1 will be considered as a group. So, once we are here, the multiplicative group is a or any additive group. Now, we understand the meaning of both of them, and it says to be cyclic group if there is an element A which is basically a part of set G only or group G only, such that for any B, any element B which also belong to G, there is some integer. We could find a integer I in such a way that all the element B can be reproduced equal to a to the power I in case of the multiplicative group, and B can be for your additive group, B will be equal to I into A. Such an element A is called a generator of the cyclic group. We write the generator of the cyclic group is like this. It is a very important property of a group. We will take an example. For example, let us come to the example number D first, then we will go up. See this Z5 star with respect to multiplicative operator and identity element 1. It will be a multiplicative group and its generator will be 5, 2 and 3. How? So, with respect to 2, you see 2 to the power 0. So, what are the elements that you are having inside it Z5 star? You are having the elements up to 1, 2, 3, 4. You cannot go beyond 5. Okay. So, you start like this 2 to the power 0 if you go and you keep on increasing the value of this I is equal to 0, 1, 2, 3, 1 by 1 you will be getting your all the elements. So, 1 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4 and 2 to the power 3 after mod 5 operation the remainder will be, it is basically 8, but if you divide it by 5 then it will be ending up with the remainder 3. So, it is a n is this is a modulo operation that will go on the numbers, and if I increase 2 to the power 4 if it is equal to 16, if I do the mod 5 operation I will end up with 1 which is the element of this. So, hence you will come back to all the elements of this group if I do the modulo operation mod 5 operation on the number systems, and hence that is the best element on which you are doing that ith operation going on, and that will be the generating element of that cyclic group. So, definitely it is a cyclic group with respect to the generator 2 generating element or with respect to a generator 2. Similar stuff holds good for the element 3. So, if I go ahead you will see that I will get all the elements back. This is equal to 3 square 3 to the power square is equal to 9, but if I do the mod 5 operation I will end with the number 4, and 3 to the power 27 with mod 5 operation will give you back number 2. 3 to the power 4 actually mod 5 operation will return you value 1. So, you are getting the values 1, 2, 3, 4 only. So, 1, 2, 3, 4 all the elements of this Z5 star here. So, fundamentally the point is I have not shown the calculation for your number 5, but you please do it by your own. You will be able to see that again you will be generating back all the elements of 1, 2, 3, 4 only within this whole operation. So, we can declare that with respect to these 3 generators, this is basically a cyclic group. Please do at home all the business with all the calculations with Z3 star, with Z6, where I have already given the generators, but you can but in exam there will be a question like given this kind of the group you have to find out your generator and check whether this kind of group can be declared as a cyclic group or not. If you do not find any generator to generate all the elements inside that group, it cannot be a cyclic group. And group, the last definition in this module is related to the finite group. Group is called to be a finite group if it contains only the finite number of the elements, and consecutively if a group is called to be infinite, that means there are the infinite elements inside that group, and the maximum number of the elements that you are finding inside that group will be called the order of the group, and the order of the group usually we write as mod of G for the finite group. For the finite number, for finite group actually we write the order to be written as mod G.